Okay. So before we continue, I just want to go over the test one. I'm going to complete the grading hopefully tonight. If not, by the end of the weekend. I'll post the long answer solutions, and the short answer solutions should be up on Master in Physics by now. And you should have your grades by the end of the weekend.
And for the labs, can I still hand in? Because I'm missing 2 more from last
you
week.
can hand them in. That's fine.
All right.
Yeah. And I'll have the labs graded by next week as well. What else? So for extra credit, people have been asking me for extra credit. I could do some extra credit assignments. I'll have them due like the day before I have to hand in the grades, and they'll be on the chapters that I miss. So the way the homework will work is that right now you'll have, if you don't do any of the extra credits, I'll drop the lowest grade. If you do the extra credits, any of the number of extra credits that you do, I'll drop the end lowest grade. So if you do 2 extra credits, I drop the 3 lowest grades. So it really works out to your benefit with the extra credit. I'll replace that with whatever whatever. If you did bad poorly on our homework, I'll replace that with it.
Professor?
Yes.
On Master in Physics, the test 1 short answer, the grades are there, but you can't like access and see the individual.
Okay. All right. Thank you for letting me know. I'll fix that.
And for the extra credits, is it gonna be like a homework, or is it gonna be like a lab, or?
Homework.
Oh, homework. Okay.
Yes. The labs are. It's a different course actually. So you get 2 grades.
All right.
So that's it. Okay. So let's finish this chapter. So look at example 1 and example 2 in the book, and we went over the vector notation of the momentum, and it's along the omega. It's along the direction of the angular velocity. So it's out of the page. And I want to introduce what the cross product is. So when I said that right-hand rule, right, it rotates around. So we figure out the direction perpendicular to our movement. Really, what we're doing is a cross product. What a cross product is, it's just a way to figure out a perpendicular vector. Now, the most general way is, let's say if we had 2 vectors and they're at an angle theta, right? And I ask you, give me a 3rd vector that's perpendicular to both of these, right? And to do this, you would do a cross product, a vector cross product, right? So let's say if I have vector A and vector B, and I ask you to find vector C, right? Now, if you look at C, it's both perpendicular to A and B, right? And the vector cross product calculates this. Now the cross product, the magnitude of the cross product is given by the magnitudes of both vectors times sine theta. And if you look at this, this is very similar to how we calculated the torque, right? And the torque is actually a vector cross product of the radius with the force. And this will give you the magnitude, but this does not give you the direction. The way to figure out the direction is by using the right-hand rule. Now here I have 3 fingers, right? We'll use this right-hand rule a little bit differently. Instead of doing the curl around it, instead of we curl around the direction of motion, we actually break our fingers up into 3 vectors. Now, in this right-hand rule, my 3 fingers represent 3 different quantities. So my thumb represents the resultant vector. My index represents the first vector in the cross product, and my middle represents the second. So, and now, if you look at this, well, actually, I wrote these backwards. It won't work out quite like how I would want it. So we have A and B. So if you look, I have A pointing that way, and B is kind of pointing into the board a little bit, and this gives me C. So I use my 3 vectors. So I have A, and this is B, and usually A and B have to have they have to have an angle between them. So and on full strength of the cross product, they're 90 degrees. So usually make A and B 90 degrees. My index finger 90 degrees. My thumb tells me the direction. So it's pointing upwards, right? You can't use your left hand, because if you use your left hand, it'll point downwards in the opposite direction. So you use your A and B, and then your thumb points in the direction of that vector, right? Use this method. If you're given the components, there's an algorithm that you have to use, and it's 11-3B, and the way it works is this. So for the I direction of our vector, we look at these terms. And then, so for C, and then we look at these 2, and we multiply this together, and then we subtract it from the multiplication of this. This is why it's called the cross product. You're multiplying cross terms together. So it would be AY times BZ minus AZ times BY. And this is your ith. And then for your J component, you put a minus sign in front, and you do the same thing with these guys. And you do the same thing with the cross terms of the J component. So instead of working with J and K components, now you're working with I and K. And you do the same process. So it's AX times BZ minus AZ times BX plus okay. So then you have this, and this is the vector. This gives you C, this vector, by doing this process. And that's the cross product. It's a lot to take in. You have to think about it. And then it obeys properties. They're on 11-4. Look at the different properties. So if you reverse the direction of these 2 vectors, now it will point downwards instead of upwards. and then it'll tell you what to do, how to add them, and the distributed law and all that. Now, if we using this, if we go back to the torque, we'll have this now. Now that the torque, now we have the definition of a cross product. I can give you the torque, and it's just it's R cross F, and it was very similar to the other formula, and it'll be applied the same ways. So, and then of course, the total net torque is just the sum of all the other torques in the system, right? And the way we relate, if you remember, how do we relate it to the angular momentum now? Well, we know that the force is equal to the derivative of P. So if we do that, if we take the torque, we know that the derivative of the torque is equal to L. So we take the derivative of R, right? And this, and the way the derivative works with cross products, you just use it like the product rule, where you take the derivative of this plus this term with the derivative of that. So here R is constant, so it would be just this, right? And then we know that df dt is equal to d. Hold on. I'm sorry, I did it backwards. I'm sorry about that. I did it backwards. So we know that, and dl is actually defined by this. It's just r cross p, the linear momentum. I could have solved it the other way. I would have had to done an integral, but I just wanted to show you the relationship between L and dt. So now, if we want to, that's not correct. I did not write that right. It's dl dt is equal to r p. Sorry for those last few mistakes. I usually don't do it. So the change in angle momentum is equal to this. And then, of course, dp dt is just equal to the force. Right. Yes, is equal to the force. And then this is, and then, of course, r cross f is equal to the torque. So we get the same laws. Right. Okay, great. Now, please review section 11-3. It's the angular momentum of a single particle, and it would help you intuitively understand why this angular momentum is pointing in the upwards direction. I described it already, but I'll skip that since it's not extremely important. So, and then we get like the conservation of energy, conservation of angular momentum. Right, where we have the sum of the external torques is equal to the change of the angular momentum. Okay. So I'll do one more problem with this, and then we'll call it a day. So we'll do example 10, 8, 11, 8. So this is Atwood's machine. So let's say if we have a pulley, we have a mass on one side, mass A, and we have it's connected to another mass on the other side, mass B.
So that's a rope, right?
Yeah, this is a rope.
Okay.
A massless rope, we should say.
Okay.
And this is mg. Right. That's the forces downwards. And this accelerates upwards, right? And this one accelerates downwards at the same speed because it's connected by this rope that's under tension. So there's no deformations. It's non-elastic. So if this one accelerates upwards, this one will accelerate at the same acceleration downwards, right? Now it asks for, hold on guys, I have to take this course since we're running over time. Give me 5 minutes and we'll continue and finish this problem, okay?
All right.
Professor, I think you muted yourself.
What is it?
Thank you. Okay, so we have a pulley of radius r, and then and it has a moment of inertia of I. All right, and in this problem, it asks for what's the acceleration of the masses, right? And that's it, actually. And it asks us to compare if we ignore the moment of inertia or not. So let's do this problem, right? So the way we'll do this problem is by using both the torque and the angular momentum, right? Now, there's a key concept from 11.3 that I want to go over real quick. Now, let's think about this, right? So let's say this is our origin. And let's say if we have a mass that's going in this direction, right? It's linear motion, right? As a linear, at some velocity v, right? Is there an angular momentum associated with this linear motion? And the
I'd say
answer
no.
is yes.
What is it?
Oh, is there an angular momentum associated with this linear motion?
I don't think so.
Well, sometimes you're right and sometimes you're not. It
Okay.
depends on where you put your coordinate system. You set your 0 to. even though this is moving in linearly, depending on where we look at our that we set our origin to, you could give this an angular momentum, right? Because think about it when it's over here. Right here at this point, it just has a tangential velocity in this direction. So at this instant, you could say that it has angular momentum, right? Because it's just tangential to the point, right? This is the lever arm, and this is the velocity. And the angular momentum is just strictly defined as this, right? Or P is equal to mv, right? So over here it's non-zero, right?
Mm-hmm.
So, and if you look at over here as well, the angular momentum will be the same, because it all depends about is this component, this perpendicular component to P. So over here, this perpendicular component is the same. It'll come out to this same. So you could give it, you can have angular momentum for an object in linear motion. And they go over this in section 11.3. I would have derived it, but it's not worth the time. But take a look at section 11.3. And so even though this is moving up and down with respect to the origin, it has angular momentum. So the total angular momentum of the system would be, so let's look at it. So this is moving upwards, right? At any given point, it's moving upwards at some velocity, right? So the angular momentum of mass A would be ma ma r squared. Remember that we have to calculate the moment of inertia relative to this for the mass if we're considering this, right? Ma squared times its angular velocity, right? And its angular velocity is related to, let me write it out first. So it's going in this direction, right? And then over here, even though it's moving downwards, it's moving with the opposite velocity. In terms of this axis, as we rotate around, it's moving in the same direction, right? So here we're actually taking the counterclockwise as positive. We could do that as long as we stay consistent. Normally you do, I mean, the clockwise direction is positive. Normally you take the counterclockwise as positive. So for B, even though it's moving downwards, it has its angular momentum is in the same direction because it's on the opposite side of the origin or the center of rotation, right? And we can relate and now let's plug in its linear velocity for omega, and right, the linear velocity is just the tangential velocity, right? So we'll have omega r naught is equal to its velocity, and then when we plug it in, we lose a term. Oh, hold on, there's more to this equation that I didn't add yet. So besides the angular momentum of this, we also have the angular momentum of the pulley, and that's I times omega, right? And now let's plug in the velocity, where x for its acceleration. So we have to plug in, we'll plug in the velocities for each of these omegas. And when we do that, right, omega r naught is equal to v. And then we have this, right? It gets rid of all these r's. V plus I times V over R naught. And this would be the total angular momentum of the system. All right. Now let's look at the external torques. So now let's get the torques on the system. So there's two torques, right? There's the torque due to mass A, or we should say the torque due to Ft, the tension, right? Or the tension in each side, right? So the torque is equal to, oh, I'm sorry, we should really, so we have MA times G down here, and these are the two torques, right? They're applied through the tension force. So we'll have the torque is equal to MBG times R naught, right? It's just an application of this force on that point. And then over here, this torque is pulling it downwards over here. This torque is pulling it downwards over here. They're both in the same direction, but they're on the opposite sides of the rotational motion, so that they're opposite to each other.
Would be negative.
Negative, yes. So then we have, now we call this direction positive. So A would be, so this force downwards over here in the counterclockwise direction is negative. So we have this situation here, right? And now we could relate the two, right? What equation are we going to relate it to? This is L. Well, we know that this is true. dl dt. So let's take the derivative of dl dt. And here nothing changes except for in time, except for the velocity. So we just got to take the velocity, take the derivative of the velocity, right? And this is equal to RO. I'm pulling out the velocity because it's a common multiple. div over here, right? And then this is just A, right? So the torque is equal to MA times A. All right, and we set this equal to our equation for the torque that we calculated up here, right? So we have these two. Now we just solve for A. Let's go up here. We'll solve for A. So A, you just divide this side by that. So it would be MGRO divided by MARO plus.
Professor,